Good morning, students. Sejanandam, continuing our lecture series of analog and digital communication subject, coming to the lecture 6 on pulse code modulation. So basically, what is pulse code modulation? So pulse code modulation is a type of signal encoding technique in which the analog information signal is sampled and the amplitude of each sample is approximated to the nearest one of a finite set of discrete levels so that both amplitude and time are represented in discrete form. In pulse code modulation, the continuously varying analog signals are converted into pulses of fixed amplitude and fixed duration. So PCM is a binary system where a pulse or a no pulse within a prescribed time slot represents either logic 1 or a logic 0 condition. So coming to the block diagram of the PCM, it consists of the transmitter and receiver both. This portion consists of the transmitter, then the transmission channel, and this portion consists of the receiver section. Let us discuss one by one block of the block diagram. Coming to the first portion, the bandpass filter limits the frequency of the input analog information signal to standard voice band frequency range of 300 to 3000 Hz. The sample and hold circuit periodically samples the analog input signal and converts these samples to a multi-level pulse amplitude modulated signals. The analog to digital converter converts the pulse amplitude modulated samples to parallel PCM codes. PCM codes are converted to a serial binary data in the parallel to serial converter and then represented to the transmission line as digital pulses. So first the signal is passed through a low pass filter for the required bandwidth and the frequency range. Then it is sampled by sample and hold circuit. Then it is quantized. That is, its amplitude is approximated either 0 or 1. Then it is encoded and sent to the transmission medium. At the reception end, exactly reverse of this occurs. That is, the transmission line or the repeaters are placed at prescribed distances to regenerate the digital pulses and enable to remove the interference, if any, due to this channel noise. In the pulse code modulation receiver, the serial to parallel converter, this regenerator circuit is the serial to parallel converter, converts the serial pulses received from the transmission line to parallel pulse coded modulation codes. The digital to analog converter or the decoder converts or generates sequence of quantized multi-level sampled pulses resulting in reconstituted pulse amplitude modulated signals. The sample and hold circuit, which is this reconstruction filter circuit, is basically a low pass filter to reject any frequency component lying outside its band. Then it converts the recovered pulse amplitude modulated signal back to its original form in this destination process. So this is how the pulse code modulation system works. Coming to the waveform portion, this is our massive signal. This is how sampling takes place. Then these bubbles shows the quantized levels of these signals. That is, it is the amplitude of the wave is approximated either 0 or 1. Then this is the pulse code modulation, which is in the form of a discrete, either the amplitude is 0 or 1. Now coming to the advantages and disadvantages of pulse code modulation. So advantages are it has uniform transmission quality, low manufacturing cost, good performance over very poor transmission paths. The disadvantages are large bandwidth is required for transmission and it is prone to high attenuation. Applications are, it is used in compact disc, in digital telephony and digital audio applications. Now, next is differential pulse code modulation. If the difference in the amplitude levels of successive samples is transmitted rather than the absolute value of the actual sample, it is known as the differential pulse code modulation. So, for the digitalization of analog voice or video information signal using pulse code modulation, the sampling is usually carried out at a rate higher than the Nyquist rate. It is observed that the resulting Sampled signal does not change much from one sample value to the adjacent sample one. In other words, adjacent sample carries same information with a little difference resulting in redundant information. DPCM is specifically designed to take advantage of sample-to-sample redundancies in typical speech waveforms. Since the range of sample difference is typically less than the range of individual samples, fewer bits are required for differential pulse code modulation as compared to that needed of a conventional pulse code modulation. Now coming to the encoding and decoding part of the differential pulse code modulation. So basically the analog input signal is band limited to 1/2 of the sample rate. So sampling takes place here. It is then compared with the preceding accumulated signal level in the differentiator. Here it is compared. The feedback loop or the accumulator, this is accumulator comprising of binary adder. This is the binary adder, digital to analog converter, and integrator. An integrator determines it and applies to the differentiator for comparison with the input signal. Then it is convenient to find whether the next difference signal needs to be positive or negative and of how much amplitude in order to bring the accumulated signal level as close as possible to the input signal. At each sampling time, the difference amplifier compares the input signal level and accumulated signal level. The resultant analog difference signal is held constant by sample and the whole circuit for duration of the interval between sampling times. The quantized differences are converted into serial binary bit stream before transmission as DPCM signals. Thus, the analog difference signal is PCM encoded and transmitted in the same way as conventional PCM system, except analog to digital converter uses fewer bits per sample. So this is the encoding part of the DPCM signal, where each signal is compared with the previous sample for its quantization to be positive or negative. Each received signal, now coming to the decoder part, each received signal is converted back to analog signal by a digital to analog converter after serial to parallel converter is stored and then summed with the next sample received. This operation is similar to the accumulator used in the transmitter. The integration is performed on the analog signals, although it could also be performed digitally. So this is DPCM. I think you have understood the difference between the DPCM and PCM. In PCM, analog signal is simply converted to a discrete form, but in DPCM, the difference in the samples difference in the preceding samples are sent as a signal. Coming to the advantages, the number of bits required to transmit one sample will also be reduced, as the name suggests, as we have discussed earlier, that the bit will be reduced as difference between two samples is being sent. Overall bit rate will decrease automatically, bandwidth will be less, and more efficient encoded signal will be obtained. Coming to the next portion, that is delta modulation. Sorry. Okay. So delta modulation uses a single bit differential pulse code modulation code to achieve the digital transmission of analog signals. In delta modulation, the present value is compared with the previous sample value. So basically, only two possibilities will occur in this. What would be the two possibilities? If the value of the current sample is smaller than the value of the previous sample, a logic 0 is transmitted. And if the value of the current sample is greater than the value of the previous sample, a logic 1 is transmitted. You can see from here how quantization takes place. Like the value of this sample is greater than this sample, so 0 is transmitted. Now the value of this sample is greater than the value of this sample, so 1 is transmitted, and likewise. Coming to the encoder portion, how it is done. So this is the basic circuit diagram of a DPCM. You can see it now very finely. So the analog input signal is sampled and converted to a pulse amplitude modulated signal. Then it is compared with the output of a digital to analog converter. The output of digital to analog converter is a voltage level equal to the regenerated magnitude of the previous sample, which was earlier stored in the up-down counter as a binary number. The up-down counter increment or decrements its count by 1 at each rising edge or falling edge of the clock, depending on whether the previous sample is larger or smaller than the current sample. The up-down counter is clocked at a rate equal to the sample rate, and it is updated after each comparison. The digital output of the counter is converted to analog quantized estimate by digital to analog converter. The sampling time is the time of occurrence of each active edge of the clock. The accumulator generates the staircase approximated, like we have seen earlier, that this is the staircase generator. It produces like stairs. Staircase approximated signal output and is delayed by one sampling period. If the input binary is 1, it adds one step to the previous output, which is delay. If the input binary is 0, it subtracts one step to the previous output. And the decoder portion is also very similar to that of DPCM. Initially, the output of the digital to analog converter is 0 volt. Output is 0 volt from here. The first sample is taken, converted to a pulse amplitude modulated signal and compared with the 0 volt. This is the delay or the accumulator portion. Okay, if the output of the accumulator is logic 1 condition, indicating that the current sample is larger than the amplitude than the previous sample. On the next clock pulse, the up-down counter is incremented. The digital to analog converter now outputs a voltage level equal to the magnitude of the minimum step size. As the logic 1s and 0s are received, the up-down counter is incremented or decremented accordingly. Consequently, the output of digital to analog converter in the delta modulated decoder is identical to the output of the digital to analog converter in the delta modulated encoder. The quantization noise is rejected by passing it through a low pass filter having a bandwidth equal to the original signal of the bandwidth. So this is how delta modulation works. Coming to the advantages, it is a simple circuit, better signal to noise ratio for speech signals. Now disadvantages, it has high quantization error, high bitrate requirement, and slope overload and granular noise. So basically what is this slope overload and granular noise? Slope overload is when the slope of the analog signal is greater than the delta modulator can maintain. It is called slope overload. Like it is a rising edge and it rises at a steep rate. So the delta modulator cannot detect the step size of this, as the step size is fixed in case of delta modulator encoder. The step size is fixed. That's why it keeps on moving, and here we can accept noise over here. So this is called slope overload distortion. So distortion takes place because the step size is fixed. It cannot follow the massive signal. So this is slope overload. What is granular noise? If the signal is constant, massive signal or the modulating signal is of constant amplitude. When the input analog signal has a relatively constant amplitude, the reconstructed signal has variations that were not present in the original signal. So we will the step size will be read as this, and the granular noise will be injected in our modulated signal. So these two drawbacks or disadvantages has been overcome by using adaptive delta modulation. So basically, let's discuss about the adaptive delta modulation. So adaptive delta modulation is a delta modulation system where the step size is automatically varied depending on the amplitude characterization of the analog input signal. So in this, the step size, which is denoted by delta, is made adaptable to the variations in the input signal in the following two ways. What are those ways? Those two ways, if the input signal is varying very fast, the step size is increased. If the input signal is varying very slow, the step size is decreased. This amount to discrete changes in the value of the step size in accordance with the changes in the input signal levels. The receiver must be able to adapt step sizes in exactly the same manner as that of the transmitter. Since the transmission consists of a series of binary digits, the step size must be derived from this bit sequence. So this is basically the block diagram of analog to adaptive delta modulation. A common algorithm is followed for an adaptive delta modulation is that when the consecutive ones or zeros occur, the step size of the digital to analog converter is increased or decreased by a factor of 1.5. However, various algorithms may be used for analog to may be used in adaptive delta modulation depending on the requirement of the particular system. In ADM, the slope overload and granular loss is reduced. How? By if the step size automatically increases by 1.5 after a predetermined number of consecutive ones or zeros. Usually we take 3, and after the next sample, if the output level of digital to analog converter is still the same level, the next step size increases even further until the output of digital to analog converter is closer to that of the current sample value of the analog signal. Slope overload distortion can be reduced how? When an alternative sequence of ones and zeros occur, the digital to analog converter automatically revert to its minimum step size. Thus, granular noise is reduced. The circuit diagram or the block diagram is shown here. It is same as that of delta modulator, except we have the comparator over here. Earlier in delta modulator, sample and hold circuit is before comparator. Here we have after the comparator. Coming to the advantages. There is a reduction in slope overload distortion, as we discussed earlier. Reduction in idle or granular noise, as discussed earlier. Wide dynamic range because of variable step size. Obviously, it changes to 1.5. It can increase its step size by 1.5. Better utilization of bandwidth as compared to that of in delta modulation, and better signal to noise ratio that of linear delta modulation. So we conclude this PPT over here only. I hope so. You are very clear about these topics. This is the comparison. What we have discussed earlier is in tabular form. Number of bits, level and step size, quantization error, bandwidth, feedback, and complexity. These are some of the points. Sometimes it may be asked directly to compare the various pulse code modulation techniques. So you can compare these 3 techniques and write in your exams. I hope so. Now the pulse code modulation techniques are clear to you through this video lecture series. And if you have any query, please comment on the comment box, and I share all the links of ADC, previous 5 lecture links of ADC in this comment box. You can go there and write or read or listen or make notes or whatever suits you. You can make an advantage of those videos. So we'll see you in the next lecture, in the next lecture series. We'll start with now amplitude shift keying. So till then, thank you. Sejanandam.